One of the fun things, for me at least, about uh, looking at covalent compounds is that if we look down at the molecular level details and the structure of those covalent compounds, we can make predictions about not just microscopic properties, but also macroscopic properties of the resulting material. So first of all, what about bond length? This is definitely a microscale property. When we're looking at bond lengths in covalence, the bond lengths tend to follow the atomic size. So if I've got bigger atoms involved in my bond, they tend to have longer bond lengths. So a hydrogen-hydrogen bond, probably the smallest element we can use, has a bond length of about 74 picometers. If I go from HH to CH, carbon is bigger than hydrogen. That bond now lengthens to about 110 picometers. And if I go from CH to CC, now it's lengthened all the way out to about 1.5, or to about 154 picometers. So bigger atoms make bigger bonds. That's probably not terribly surprising. The other thing that we looked at a little bit is what about some of those multiple bonds? Multiple bonds, you can think about bonds almost like little rubber bands holding these atoms together. The more rubber bands we have, the shorter the bond gets. So if I don't change anything else, what if I just look at carbon-carbon bonds? A single bond, refer to that as having a bond order of 1, is carbon-carbon. We said that was 154 picometers. If I go to a double bond, that's a bond order of 2, now that bond has shrunk down to 134 picometers. And if we go to that triple bond, bond order 3, now it's tightened up even more. It's shrunk down to about 120 picometers. So we can say something about the size of molecules just based on how they're bonded together. Another important thing to look at is this idea of polarity and polar covalent bonds. So when we've got an ionic interaction, we've completely transferred electrons from one species to another. In a pure covalent bond, electrons are perfectly shared, but they really can only be perfectly shared if the two sides only attract them equally. What if the two sides of the bond have unequal attraction for the electrons? So we're looking at something like hydrogen-hydrogen, again, both of those hydrogens attract the electrons the same amount, so this should be purely covalent. But if we look at something like HF, fluorine has a very, very strong attraction for electrons. So the electrons involved in this bond are being attracted to the fluorine much more, which means that the fluorine side of the bond is going to have a little bit more electron density, is going to be a little bit negative, and the hydrogen end of that bond is going to be a little positive. So this is what we mean when we refer to these as polar covalent bonds. They've got a dipole where one end is partially positive and one end is partially negative. How do we predict that? Well, fortunately, we've got a really nice tool called electronegativity. Electronegativity is the strength with which an element attracts electrons in a covalent bond. It sounds like exactly what we need. And if we look at the periodic table, it is a pretty consistent trend on the periodic table. As I go from left to right, things get more electronegative. As I go from bottom to top, things get more electronegative, which means fluorine is the most electronegative element on our standard periodic table. So fluorine always will pull electrons stronger than other elements. That means we can use electronegativity as a way to assess the type of bonding we're working with. So if there's no electronegativity difference, remember, electronegativity is how strongly they attract electrons. If there's no difference, or a very small, so if the difference is 0 to 0.4, those are our pure covalent, or at least nonpolar bonds in general. If the difference in electronegativity is 0.4 to 1.8, Those are the polar covalent bonds that we just talked about. And if the electronegativity difference is greater than 1.8, those are the things that tend to just transfer the electron completely and form ionic compounds. So we look at a couple examples. What about a carbon-oxygen bond and a carbon-sulfur bond? So I pulled the electronegativities off that table. Carbon has an electronegativity of about 2.5. Oxygen has an electronegativity of 3.5. Sulfur has an electronegativity of 2.5. So for a CO bond, the difference in electronegativity is 2.5 to 3.5. It's 1. This is definitely a polar covalent bond. For carbon and sulfur, well, those electronegativities are the same. So carbon-sulfur has an electronegativity difference of 0, which means that that's a nonpolar bond. So carbon-sulfur is actually pretty purely covalent in the way of bonds. How do we use this? If a molecule has polar bonds, does it mean it's a polar molecule? Not necessarily. Now, it might be. In order for a molecule to be polar, there has to be at least one polar bond in it. But we can think about molecular polarity kind of like a tug of war. If we've got two equally polar bonds that are exactly opposed to each other, then those poles will cancel each other out. They'll balance each other out so that overall the molecule is not polar. If they don't cancel each other out, well, then we have a polar molecule. So a couple of examples here. Water molecule, because of the shape of a water molecule, we'll get more to that later, these dipoles, these polar bonds, reinforce each other. They don't cancel each other out. So water is a polar molecule. Carbon dioxide, on the other hand, carbon-oxygen bonds are quite polar, as we just said, but these are quite polar in exactly the opposite direction. So these cancel each other out, and this is not a polar molecule. We can use polarity, we can use molecular polarity to make a lot of predictions because polar molecules tend to stick together more strongly. So things like boiling point, melting point tend to go up when we've got a polar molecule, which is why, specifically if we think about water, water is a tiny, tiny molecule. If it weren't polar, there's no way it would be liquid at normal room temperature. But the polarity of water is what sticks waters together and makes them liquid at room temperature. We'll keep looking at these as we move forward, but again, look for differences in electronegativity and use those to predict the bond polarity and the macroscopic properties that we might see because of that. See you next time.